Hi everyone, we are happy to continue with Professor Gurari. Professor Gurari is an assistant professor and director of the Image and Video Computing Group in the CS department at the University of Colorado Boulder. And her current research interests span computer vision, machine learning, human-computer interaction, accessibility, and biomedical imaging analysis. And Professor Gurari's research has been supported by the NSF, Microsoft, Adobe, and Amazon. And she received her PhD from Boston University and was a postdoc in UG Austin, and then became an assistant professor in the School of Information at UG Austin. And thank you very much, Professor Gurari. We can get started.
Thank you so much for the invitation to speak to everybody, and thanks to everyone for showing up for the talk on quality issues and images taken by blind people, as well as to talk about the implications of those quality issues for AI that describes the images. So why do I want to share about this? The motivation is that as today, there are real users, being people who are blind, who want on-demand visual assistance. On the slide, I just show 4 examples for dirty. What flavor is this? What type of pills are these? Please describe what you can see. Are the kinds of information that might be trivial to people with sight, but for people who are blind. And so already real users are relying on kind of on-demand visual assistance. Take a picture, optionally ask a question about that picture, have that sent off to remote humans who in turn will provide an answer if a question was asked. And so I just show on the slide a few of the different applications that have emerged over time to provide this kind of support. This includes VizWiz, Be My Eyes, Ira, and Be Specular. And just to give you context of how many people are using this kind of service today, as of 2021, there were thousands of users of Ira, thousands of users of Be Specular, and 250,000 users of Be My Eyes. And that's just a drop in the bucket of the potential for the number of users. There's an estimated 39 million people worldwide who are blind. So there's really the potential to have far reach with these kinds of applications. What's the motivation for using AI? We know that there's a lot of limitations for relying on humans. Like humans are constantly and the privacy issues that humans in the loop. And so a lot of the goal of this work is to teach computers to automatically describe images taken by blind people. I believe, and hopefully I'll convince you by the end of this talk, that many people would find this important. I believe that success with images taken by people who are blind, they translate to helping with analyzing images from other kinds of photographers that have similar abilities. So thinking about robots that similarly have just 2 cameras where all the intelligence comes from what us as developers embed in them, little children who take photos, as well as wearable devices. I also advocate for yourselves. One of the things that happens with sight loss is that is on onset as we age. And so you might be developing for future you or your siblings or your friends as you develop this kind of work, if you so desire to jump on trying to improve algorithms for people who are blind. And then of course, there's situational sight loss where we can benefit from having a little bit of assistance. And so with that, what I'm going to go over for the rest of this talk are 3 parts. First, I just want to introduce what are the AI tasks for describing images taken by blind people and real use. Talking about what are the quality issues that we know are common for images taken by blind people. And then I'm going to end with a discussion about the AI models and techniques for overcoming quality issues. So with that, jumping in. So the tasks for describing images are twofold. One is captioning. So for this image, something like a bunch of small light brown mushrooms in a green field. For answering visual questions, was poisonous. So just the background for how AI challenges work, you have sort of large data set where you have images, and we want to take our large data set and split it into a training set and a test set with the target responses for the test set hidden, so that teams can submit algorithms, predictions on the test set to evaluation servers to see which algorithms do the best. And so with that, our team embarked on building a challenge for a real-world application. We leveraged data from over 11,000 people who submitted over 70,000 requests to what's called the VizWiz mobile phone application. And this was between 2011 and 2015 when these requests were submitted. We were able to use about 62% of that data because the purposes to improve upon the technology for describing their images. This is real world applications. So we had to anonymize the data. So we transcribed all the questions to remove people's voices. We resaved images to remove metadata, such as where they're located. We went through all the images repeatedly to verify that there's no personally identifiable information. We came up with a category of about 23 different privacy categories to remove, and that includes things like people's faces, their prescription pill information, as well as information in their mail, such as social security numbers, bills, and much more. And then finally, we went to the crowd and we asked them to produce for us high quality captions, as well as answers to the questions that were asked. And the result is 2 different data sets, one for visual question answering, which contains 10 answers per image question pair, as well as over 39,000 images with 5 captions per image. So at the time that we released these data sets, these were the first publicly available data sets where individuals requested image captions and answers to support their real daily needs. So just of note, this is a different scenario for data set creation than mainstream data sets. I know this workshop is about understanding real world challenges. One of the real world challenges just from the data set creation is that you can't do what mainstream data sets do, which is to go either and collect images from the or synthetically creating images. And then we also can't make up questions by asking crowd workers to just make them up or use computers to automatically synthesize those questions. So before jumping into the quality issues, I just want to give you a sense of what is the information that blind people are seeking. And so here I show on the slide what were the most popular questions that were asked when questions were asked. We see that the most common question is, what is this? And here I just show a few examples of the images for which this question was asked. So you see things like a remote control. It appears there's medicine on the bottom. We can see there's some pictures of scenes, food such as pizza rolls, and a can of food, seemingly beans. Other common questions included, what is in this can? What does this say? And what color is this? And so for examples for each of these, we see what is in this box is the question. And you can see we have boxes mostly of food. So we have things like fudge brownies, macaroni, and then we also have things like Tide bleach for cleaning. For the question, what does this say? That can span anything from reading mail to reading about food and drinks, to reading menus, as well as computer screens. Insofar as what colors this, I show examples on the slide, and mostly that question has been asked about people's clothes, ostensibly to help them decide what to wear for that day. If you're interested in exploring real people's data a bit more, we do have a live website where you can go and you can review all the images. And then for the different images, you can click on them to get a sense of what does the metadata look like, including the visual questions, the answer data as well. So this is all a backdrop for us to think about how do we make automated algorithms that solve a real world application. And so we did what is standard in the community. We set up public leaderboards to track algorithmic progress. And so teams can see where they fall within the international rankings. We also established an annual CVPR workshop to celebrate progress. We actually have our workshop going at CVPR. And so that's it for what are the tasks that are driven by a real world application. So now jumping into what are the quality issues that we observe from this real world use case. Hopefully it's evident that the challenge for people who are blind and taking images is that they cannot verify the quality of images they take. So it should be clear that there's going to be some differences in the pictures that we're going to see from this population from experienced sighted photographers. And we wanted to quantify what are the differences. So we did a few when we allowed people to provide a caption. We notified them that they could specify that the quality issues in the images are too severe to recognize the visual content. And so when someone was making a caption to an image, they could just say copy to description, and that was the pre-crammed language we had. The other thing that we did is we asked the people when they were reviewing images to let us know what are the quality issues that are observed in the images. We provided it as options: blur, so is the image blurry? Bright, so is the image too bright? Dark, is the image too dark? Obstruction, is the scene obscured by the photographer's finger over the lens or any other unintended object? Framing, are parts of necessary items missing from the image? And rotation, does the image need to be rotated for proper viewing? We also allowed for users to offer other kinds of issues that they saw beyond what we had identified a priori. And then they could also specify when there's just no issues, meaning that there are no quality issues observed in the image, looks good. What we observed across the over 39,000 images where we collected all this metadata is that over half of the images suffered from one or more quality issues. The slide just shows examples of each of the quality issues that we were looking for. So we could see a blurry image, a too bright image, a too dark image, one where the framing is not of the content of interest. So it's showing more of the hand and not enough of the bottle. We see an obscured case, and then we also see where the image needs to be rotated. When we quantified how often each of these kinds of quality issues occurred, what we observed is that the most common flaws are going to be image blur, occurring for 41% of the images, as well as inadequate framing, which occurs for 55.6% of images. You can see that there are other categories that are actually quite rare. So bright images occurs for 5.3% of images, too dark of images occurs for 5.6%, and obscuring occurs for 3.6%. Insofar as being able to even simply recognize what is in the images, we found that for 14.8% of the 39,181 images, the quality issues were so severe that the content could not be recognized. assist. So with that, now I want to jump into what are the models and techniques we can use to overcome these kinds of quality issues. What I argue is that there are a spectrum of solutions, and our team has embarked on addressing the spectrum where it includes preventive, so guiding photographers to take better images, to reactive, to AI for describing images with quality issues, and then in between to each of these. In the case of preventive, the goal is to help a user understand what are the quality issues when the photographer is taking the picture. And so as a foundation for this work, we wanted to know, can existing techniques that exist for help a user know whether the content in the image is recognizable or not? What we found is that existing techniques do a terrible job of differentiating whether the content in an image is recognizable or not. Okay, so we looked at 6 different methods, and what you can see is there's a high overlap on the distribution, which means basically we can't separate recognizable from unrecognizable with these techniques. We actually want to see those 2 distributions totally disjoint. So that prompts the need for new algorithms that can work well with images from people who are blind. So we actually embarked on that. We found that the algorithm and so we tried some more traditional techniques based on SIFT and HUG features, where we throw a linear SVM after those features. We also tried a 2-layer neural network. What we found is across the board, when we look at 3 different evaluation metrics, we can get pretty good results from such basic architectures. And so this suggests that it should be very easy when a photographer is taking a picture to just notify them, hey, you've got some issue with the picture, try again. We also wanted to do better than just notifying a user of whether the image is recognizable or not. What kind of quality issue occurs? So we, again, have categories of blurry, too bright, too dark, and so on. So we, again, tried some simple algorithmic frameworks. In this case, we tried a 3-layer neural network using exception features. And then at the final layer, we have 8 sigmoid functions, so that for each of the quality flaws, as well as the no quality flaws choice, we could just flag, hey, this quality issue occurred or not. We again found that across 3 different types of evaluation metrics, we can get a very good job of notifying photographers what are the quality flaws that occur in their images. One thing I like to note is that the performance is worse for flaws, but overall, we do find a good ability to notify photographers about quality flaws. All the data that was used to build the 2 sets of algorithms I described are publicly available. Better algorithms that could then be used to assist photographers to take good pictures from the get-go. Just with that said, I do think there's still an open question of how do we effectively guide a photographer using this information of the quality flaws. It sits a bit on the human-computer interaction side and that community, but basically we need to know how to interface with end users to help them know when they find out the image is unrecognizable or the quality issue, how to improve that image taking skill. And so I'll plant that seed for anyone that's listening and interested in this direction of work. Of course, if there's no issues, then move forward with captioning and preventing low quality images is one extreme. The other extreme is reactive. So let's accept that these images are going to be having quality flaws. And let's design AI that robustly can describe images with quality issues. For the data set challenges we put out there, that is what all the teams have had to contend with. We have had over 60 teams who have participated in our captioning and VQA challenges, where part of what they need to do is make sure their algorithms robustly handle these kinds of quality issues that naturally emerge for the photographers. This is a summary of what are the basic architectures people are building off of. To date, the predominant architectures for captioning have included an encoder, so describing the image using some sort of feature representation. Then attention is used to focus in the image on regions that are more salient into a representation that can be decoded into a sentence. Insofar as VQA, or visual question answering, the architecture looks pretty similar. Again, we are taking an image and we are encoding it into some sort of feature representation. Often attention is used to identify on the image what are the regions that are really important. And then that is paired with an encoding of the question to figure out from the question, hey, this is the set of regions I should look at, such as what's in the background. Hopefully the combination of the background with encodings of different parts of the image would help someone to know to attend to the background regions and what a background means. And then that information gets decoded out into a prediction, where the prediction is from a predefined list of answers, often 3,000 answers. That means, of course, that methods can't handle providing an answer if it goes beyond that scope. Over the years, what we've seen from these 60 plus teams is that the key innovations that are leading to better outcomes on lower quality images include data augmentation, such as rotating images, and then improved pre-training. So the pre-training has been done not only on larger data sets, but on data sets where the images are coming from mobile phone cameras. And so things like LexSmart were trained on massive amounts of cell phone images, which mimics what we see from our photographers of cell phone images. And so we have seen tremendous improvement over the years where models are now outperforming human performance. With that said, we have a question of, well, how are they doing with respect to different image quality levels? And so to assess that, what we've done over the years is we've monitored how they're doing based on how many people from the 5 crowd workers that provided captions used the pre-canned text of quality issues are too severe to recognize visual content. So we said if no one selects this, then it's an easy image. But if 1 to 2 people select that pre-canned text, then it's a medium quality image. And here are just some examples on the slide on the left where you can see the medium quality images. And then we said for high quality images, it's where 3 to 4 people selected that pre-canned text. And you can see on the right examples of very low quality images. Over the years, what we've seen is that the captioning models have struggled on the medium and the hard examples. So the cases where those quality flaws are deemed to be pretty high. And that's true across all the different teams. So here we just show results from 4 teams from last year. And across the board, they do much better for clean images where all 5 people said, hey, this can be captioned. And the performance gets worse and worse for the lower quality images. So I do believe even though we've hit human performance, we still have a niche where we have to do better for where quality flaws are arising. Interestingly, we see a different trend for visual question answering. So for low quality images, these are very low quality. This would be unrecognizable, but the trend, what we're seeing is that models consistently performed better on images with quality issues. The reason for that is because the answers were often unanswerable. And so that's the reason that we're seeing this difference, is that because We allow in VQA for people to say the answer is unanswerable. So with that, again, I think that there's still open space for research here. And I just want to touch on what I think are the open opportunities. And my team has touched a little bit in this as well. I think we still have a lot of work to do on how to train models that handle rare quality issues in the data. I mentioned earlier that we see that some quality flaws happen a lot, such as blur and framing, whereas others don't happen a lot, such as obscured images, oversaturation and undersaturation between the too bright and the too dark images. So I do think that this issue of not having large amounts of training data presents a problem for our community. And compounding that is that we often will get combinations of these kinds of quality issues in practice. So we'll often see that we'll have both blur and bright, or blur and dark, or blur and obfuscation, or blur and framing, or blur and rotation, and bright and obstructions, and bright and framing, and so on. Those combinations amplify the problem because we even have fewer examples representing all those quality flaws. We know real world data is hard to come by. And so how do we make progress when we don't have a lot of examples in our real world data sets? And so my team has made some research in this direction, but we struggled to find an answer. And so I would pose this for the community, thinking about how do you generalize from a few examples that you can do well when you see these kinds of novel yet rare quality issues in other spaces. All right, so now diving into the final AI component, which is editing images. We have started a little bit of work on thinking about how do you just edit those images when you get low quality data before you pass it off to an algorithm or a viewer. And so part of this means how do you automatically locate the patches where you have issues, such as here, how would you automatically locate the obstruction? And then how do you in-paint some sort of edit to this region? Or how do you automatically locate when there's some sort of rotation and fix the image, and so on. So I think that that's one really interesting direction. And our team has made some progress on a related problem to this, where we actually try to increase our data set size by saying, let's use images where there was private content. So things like credit cards, we removed out the credit card numbers and we in-painted with different in-painting techniques. So again, we're editing the images. In this case, it was to increase the data set size because in a real world application, you just don't have a lot of data. But you can imagine extending this for just editing images for any purpose, whether creating data sets or helping people just take better photographs. And so finding the patches where there's some sort of an issue and then developing and painting algorithms to improve upon the original content so there aren't corruptions. If you want to work on this kind of technique, we do have a visual privacy data set out there that you can use for this purpose. So with that, I would like to wrap up. There are many people who I'd like to acknowledge. We've had many mentees over the years. I have some colleagues who have been fantastic in supporting this work. Then there's those who have provided support with the VizWiz application, the crowdsourcing, the evaluation server. And then we've had thousands of crowd workers who've contributed tens of thousands of hours. And finally, we have received funding from NSF, Microsoft, Adobe, and Amazon for this work. So I want to leave you with some thoughts about potential next steps. We do have a website that you can visit at bizwiz.org. And just a call to action. You can learn more about the technological needs of blind people and what happens in this kind of real world application by browsing the data set at this website. You can also join our many VizWiz challenges for designing algorithms for blind people's data. Inherent in that is you have to deal with the quality issues that emerge in real world applications. And as I outlined in this talk, there are a wide range of them, and they can occur in combinations, which makes the problem very challenging, but very fun. I would encourage you, if you're from industry or you're about to go to industry, to think about how do you deploy these inclusive algorithms for the benefit of society, not just for blind people, but arguably for robots and any other photographers that similarly struggle to take high quality images. And finally, we have an annual workshop, so you're always welcome to come and join our community and hear what we have to share at our workshops and contribute what you have learned. And so with that, I know we have a little bit of time left. I very much welcome any questions from the audience. Thank you so much for your attention and attending this talk.